Yeah, so in the next chapter, I now want really to go a little bit in the direction of neural networks, because I mean that's maybe what is the most interesting thing to understand. And random matrices are somehow related to building up neural networks and maybe also trying to understand it a bit. About random matrices, we can understand quite a bit. Neural networks, really to understand them is not so easy, but at least we will at least try to get at least a few mathematical rigorous things about them. So let me maybe recall again first what neural networks are in general, and then I want to concentrate quite directly on maybe a very modern issue in this context, which is called double descent. Double descent, which is observed in general for neural networks. And I mean, to understand it, it's maybe in general a bit too hard, but we at least can get maybe some idea of it in maybe the simplest neural net, which is very trivial and which is actually a very classical stuff, namely linear regression. Okay, and just to see what we have. Okay, so what is a neural net or neural network? I mean, in German we usually say neuronales Netz. In English it seems neural network is the more common issue, but neural net seems also to be okay. But anyhow, so I probably usually say neural net. Okay, so this is a special function. I mean, this is a function from usually a high-dimensional space to, let's say, to R, which has a very specific form. So it's a function. So a neural net is a function f, which goes, let's say, from R to the P and maybe to R. Of course, I could have here more components. I could also go to a high-dimensional one, but it's of a specific form, which essentially is built out of matrices and some specific nonlinear functions. Okay, and now, so I'm now drawing the usual picture, but actually I'm drawing the picture from right to left. So my input is here, because if I'm writing down my matrix operations according how we write it, I mean this fits really that essentially you're working in this direction. So let's say I have here my input. So this is the R to the P. And then, I mean, you have operations where you act with linear mappings. Maybe you map this to higher dimensional space or a space of some other dimension. Let me say this is maybe an R to the M. And you have linear mapping here. So essentially you have a matrix which maps this to this. Where essentially you have all connections. So let me call this W1. This is just a matrix, a linear mapping going from here to here. And then you also apply in general nonlinear mappings now, but you do this component-wise. So you apply here, you have here a vector in R to the M, and now you apply a nonlinearity, but you do it component-wise. So in the beginning you are given a nonlinear function from R to R, let's say, and then you just apply this component-wise. So essentially you stay in the R to the M, and you apply a nonlinear mapping, but a specific one which just acts on the components. So very often this is called sigma or something like this. Okay, and then this is the first layer of your net, and then maybe you go on and you have the same again and again. So you have again linear mappings going to the next layer and so on up to some point. So let me say maybe here you have a matrix W2, here you have WL. L is the number of layers. It's the length, or actually it's the depth of your network. And then maybe here again you have your nonlinear mappings, sigma. And then in the last step you go down now with a linear mapping again to R. So I mean now you just go to R, so you just get here one number, and you just go down here. So in principle this is again a linear mapping. It's given by a M times one matrix, so essentially a vector. You take the inner product with a vector here. And let me call this here W, a small w. So maybe here you are still in R to the M. Of course those guys could depend on the layer you consider, but maybe let me keep it like this. Okay, and the action of the function is going in this direction. And I mean, you can write the function now just as the composition of all those mappings. So I mean, the y which you get here, which is f of x, if x is your input vector in R to the p, so this is given. So in the last step, and essentially it's matrix multiplication, and in between you do those nonlinear functions on the entries. So you do this here, sigma wl and so on up to w2 sigma w1 of x. So you start with x, you apply this matrix w1 to it, then you get a vector, and of this vector, I mean, you take this sigma. And of course, you have to read this in a way that you apply this sigma entry-wise to the vector which you have gotten here. So this sigma is our non-linearity, but it's an entry-wise action on vectors. Okay, then you multiply with this and so on. You multiply here again. You always have the sigmas taking this, and in the very last step, you just take the inner product with this guy. So this is now a row vector. So this is this here, let's say, is a row vector. So this is in RM cross 1. So essentially, you take here the inner product with this vector. Okay, and of course, those, I mean, this here is a mapping from R to the P to R to the M, and the inner ones are mappings from R to the M to R to the M. So they are all matrices. Good. Okay, but now in general, usually we are interested, or maybe we want to understand not just having one input, but we take more input. We have data of input. So actually, we calculate this here maybe for an input x1 up to an input xn. So we feed x1 up to xn, vectors in R to the p in our neural net coming from this direction, and then we get outputs. And now, of course, we do the usual thing. We collect the inputs into a matrix and the outputs into a matrix, and then the relation between those output matrix and input matrix is more or less the same as we had it here. So, I mean, if I'm writing y as the output matrix, which here is just a vector because the y's itself are just numbers, they are in R1. So this is just a 1 times n matrix. But the input guys, they are given, this is our data matrix, as we also considered it for the Marchenko-Pastur. So I'm putting all the p-dimensional vectors as columns here, so I get a p times n matrix. And then, of course, I can also say that this y, this matrix, is more or less the same function of this type applied to my input x. Namely, I do exactly the same thing. Namely, I take w sigma wl up to w2 sigma w1, and now instead of the little x, the vector, I have here my data matrix x. And the only thing which I have to interpret in the right way is the sigma. The sigma does now not act on a vector, but it acts on a matrix. But again, I'm just doing it component-wise. So I mean, if I have a sigma like this, then if it acts on a matrix, it just takes the sigma of each matrix. And of course, if I specify this to a vector, this is what I had before. Okay, and of course the w's, they are linear mappings, and if I multiply them, my matrices, with a vector or with a matrix, of course it's also it's clear what this means. Okay, so here the sigma is now the entry-wise action on matrices. Good. Okay, so that's my neural net in general, and of course, I mean, yeah, so it's in principle it's just a function in high dimensions. Of course, so usually p or so is high. That's a important point, which is of a very specific form. But it seems those functions are very powerful for capturing a lot of things. And so, I mean, of course, there are now different questions about such a network, and maybe one, which is mathematically maybe An easier one is namely if we are given such a network, so if we have fixed all these matrices and these W's, then what is the effect? So what is in particular the statistic properties of this? So if I'm feeding in a data matrix, what comes out? In particular, if I have statistical information about the X, what can I say about the Y's? So this is a question which is mathematically at least attractable in this generality. So I mean that's a question. So namely given, so if we are fixing a net, given a neural net, so I have fixed all these W's and also the sigmas, so given a neural net, let me say F, so what is the relation between input X and the output? Okay, and the relation, of course, I mean, usually you're asking for kind of probabilistic relation. So you assume that you have some probability distribution for the X's. What can you say about the distribution for the Y's? And of course, as we have seen, I mean, if we really want to be able to make precise statements, we should go to an asymptotic regime. So I mean, the numbers which we have there, P and M, and so they probably should be large. Because only asymptotically, like for random matrices, we are able to make precise statements. So I mean, so what we want to understand here is this relation, and we want to have this probabilistically, and of course asymptotically. Okay, and of course, I mean, if I only have one matrix here, just a W1 and nothing else, then it's more or less like we had in the Wishart matrix context. Then it's questions like this. Okay, and there are statements of this form, and maybe let me write it down. So I mean, I'm not going to talk about this, at least not now. Maybe I come back to it later. But so I mean, one important statement in this context, which can be proved rigorously, is that random neural networks, and random means that I'm choosing all those weights, these W's, also in a random way. So random neural networks are in the infinite limit of infinite width, and the width is this M here. So each layer has a width, M, and if I make this going to infinity, then the size of my matrices goes to infinity. That's the large size limit of random matrices, where we know that we should expect something nice. So the width is this M, and the depth, usually the depth which we have in deep learning, that's the size L, how many layers I have. So the depth is a bit more mysterious, what the role of this is. So the width is more accessible, because this really is related to just having a random matrix and letting the size of this go to infinity. And so there are statements here that random neural networks in the infinite width limit are Gaussian processes. Okay, so I will not be precise what this means, but if I'm putting in Gaussian vectors, then what I get out and what I can control in all steps is also of a Gaussian nature. And Gaussian things are governed by the mean and their covariance. And one can see how this goes through the network. Okay, so maybe I come back to this at some later point, but maybe at the moment this is a mathematical nice statement, but it doesn't tell maybe not so much about why neural nets are so powerful. So, okay, so maybe the second question, I mean, that's the one which is, of course, for applications and really what you do with a neural net, much more interesting. So, namely, not start by saying, okay, we are given one and I want to understand what it is doing, but by trying to construct one which does a prescribed task. So, essentially, you have a collection of input and output, and you want to construct a neural net which realizes the relation between them. So that's of course what is done if you train a neural net. So how can we construct a neural net This means how should we choose the parameters, all those W's, such that it approximates well a functional relation between x and y if we are given a collection of x's and y's. So for given training set x and y. So we are given some data as x, and we know this should have the output y, and then how do we find a function f of this form which has exactly this relation. Okay, so this is the training that it is trained to do this, but then of course what we expect from our neural net is that we could now apply it to other data set x, and then it should also give us a meaningful answer. So I mean it should not only remember what it was trained, but it should have learned things in such a way that it gives meaningful answers also for unseen data before. Okay, so this means that it also generalizes to unseen data. Okay, and of course one has to make precise what this means. Okay, but so I want to go a little bit in this direction, and the point of these neural nets is that actually they seem to contradict the old philosophy about learning and overparameterization. So I mean, there, of course, how do you approximate data by functions from some function classes? This is an old problem in mathematics, and there's a lot of statistical stuff about this. But somehow the idea there was that actually you should not overparameterize. So that's the dictum from classical learning theory, which is challenged by neural nets. So neural nets seem to be much better, doing much better than you would expect from the classical perspective. And I mean, that's the very strange thing which one really wants to understand. And I mean, at the moment, one doesn't really have a full understanding, but at least one is trying to go in this direction. So, but let me first describe what this means. So neural nets challenge somehow the classical ideas about learning. Okay, so what are these ideas? So I mean, essentially the idea is that you have a set of functions with which you want to approximate the data which you have. Okay, and you look on the errors which you make. So what are the errors? And then so you have parameters in your system which you can adjust. So you want to choose the parameters so that you get the training data. So I mean, here in the neural nets, I mean, we can choose all those W's, and we can have many of them. Okay, but classically the idea is that of course, you have parameters, so you should try to get the relation between the input and the output for your training data right. But if you only have few parameters, which means you have only a small class of functions which you can use, and you have many such connections, then of course you cannot really fit them so well. Maybe you can only approximate them. And then you make, in the beginning, if you have a very small class of functions, maybe only linear functions. Of course, with linear functions, you cannot approximate so well very complicated stuff. But so then your training error is bad, but it goes down essentially. And at some point, you have so many parameters that actually you can exactly get the relation at the points which you are given as your training data. If you have so many parameters, more or less as you have your training data, then you can really just memorize the things which you have seen. Okay, so and then of course, I mean, having more parameters doesn't improve this anymore, but of course, just memorizing is not what you're interested, but you're choosing a function which does very well for the training data, but then you put in other values, and you want to see how good is now this maybe approximating or prescribing or making prediction for what you get. And there the idea is that actually, so this here is the training error, which means you're trying to get the training data as good as possible. But if you have enough parameters, at some point you can do this. There's no error anymore. Okay, but then if you apply this to new data, then, I mean, in the beginning, of course, you're also getting better. But then at some point, it turns out that actually you fit the given data very well, but what it does in between might be very wriggly or whatever. It doesn't seem to be connected with, it doesn't seem to give a good interpolation. So actually then at some point it's getting bad again. And at the point where you really have a total, let me say a total description of all the data which you have, then actually the prediction is very bad. So this here is the test data. Okay, and so I mean, so this here, this seems to be the best point where you should maybe choose your function. So I mean, here you have essentially the complexity of the class of functions which you consider. So this corresponds to the number of parameters in your model. And if you only have few parameters, you cannot really fit your thing so well. So that's usually the underfitting regime. You can maybe do some approximations, but if you have few parameters, then they won't be very good. Okay, if you have more parameters, they are getting better and better. But then, if you have too many parameters, so that you fit exactly, you get exactly the points, then actually the prediction power of this is very bad. So I mean, usually, I mean, if you say you have a number of points for polynomial interpolation, so if you want to interpolate or approximate a number of points with polynomials, then of course we know that if I have a degree 20 polynomial, or if I have 20 points, I can fit those points exactly with a degree, 21 polynomial. Okay, and so this polynomial will be exactly at those points, but in between it will be very going up and down. So this doesn't have a power. So this means, I mean, you should not take a polynomial of degree 21, but a smaller, I mean, maybe a linear polynomial is too small. So there you will be there. But if you go a little bit higher, then maybe you have a quite good approximation. But then you're getting bad, and if you take as many parameters as you need for fitting exactly, then it's really it doesn't give good predictions. So this here is the overfitting regime. Okay, and this is usually then, I mean, this is overparameterization. You have too many parameters. Okay, or that's the classical thing. I mean, if you have as many parameters as you need to do exact description, then actually you get a very bad thing. Okay, but now the point is, I mean, neural nets don't care about this, and what people do is, I mean, they take a thing like this, and usually you take really many parameters. You have the W's, and maybe if you make your net very deep, I mean, you have many matrices there, and usually you have many more parameters than you would need to fit exactly your given data. Okay. So classical theory would say, okay, don't do this. This is bad if you put in more and more parameters. It only will get worse and worse. But if you do this with neural nets, it seems it's getting much better. That's really the success of neural nets, that you really should overparameterize. And so actually this curve here, the classical curve, is now in modern statistics. So in the last, I mean, this is something which in the last 10 years or so was somehow observed, that actually you should really go much more in this direction, and then you see something interesting more. So the typical thing you see at a neural net is something where you get here something where you improve again, and the whole curve is then usually called a double descent curve. Okay, so I mean, so actually we go over to this, to double descent. And those things are, I mean, maybe a few names, so Belkin and co-workers, or Mai and Montanari. So those people who looked on this and tried to understand this also a little bit theoretically. in practice this was of course observed before, and maybe it was also observed a bit longer before, but it was not really put so much in the center of interest. So I mean, those are works which are about 2018, 19 or something like this. So just a couple of years ago. And so what is the idea there? There you get actually, I mean, you really go more in this direction. So maybe I draw the same picture again, but I'm not stopping here. But I overparameterize, which classically people say, okay, you shouldn't do this, and we didn't really look on this so much. But so the idea is now that you get this test error, which somehow here at the point where you really, let's say you interpolate your given data. Interpolating means you really get the points which you have exactly, and then you want to know what is in between. So this is then maybe called the interpolation threshold. Okay, and I mean this here is the classical regime, which I had there. So here, I mean the training error goes down, and then of course it remains down. So this is the training, but the important one is the test error. And here it seems that if you now overparameterize, then suddenly you are getting better again. So you get pictures like this, and you might get on this side better than on this side. And so this here is the modern interpolating regime. Yeah, and so this is somehow the underparameterized regime, and this is overparameterized. And the point is that overparameterization seems to be a good thing. And maybe I want to go a little bit in the direction of trying to understand this. And so, I mean, of course, to calculate something for such a full model is at the moment not really clear how to do this, but I want to look on maybe the simplest neural net, which actually has no hidden layers and which also has no nonlinearity. And so this actually is just a good old linear regression problem. But linear regression fits somehow in this, and maybe you can see parts of this in this picture. And that's what I want to show in the following, how you can see maybe this difference between between this underparameterized and the overparameterized regime. So what I now take is essentially such a neural net where I'm throwing away everything apart from this very last guy here, this W. So it's just a linear, and this is linear. There are no non-linearities, and also there are no W's in between. And this is just a classical linear regression problem where I'm trying to approximate given thing by linear relations. Okay, and of course this is and if I have a neural net, and where usually I do the training by gradient descent, then I would just learn this guy here. And that's also in neural nets considered as not maybe the main part is missing, namely the main part seems to be that I'm learning what are the W's. Okay, and so I mean this is usually called feature learning, because what I get at this point, these very often are called the features of my data. So I'm calculating some interesting quantity of my data, different ones, and this W is then just taking a linear combination of them, and I just have to adjust the weights for each of the features, how I want to make my decision. Okay, but usually feature learning is considered as the main thing which happens in neural nets, which means I should also learn those guys here. Okay, but so now I don't have them. So in particular, I don't have feature learning, but nevertheless, I think we can see a little bit about this. Okay, so I'm looking on the simplest situation where the y is just calculated from my vector x by just taking inner product with some vector w. Okay, so this y f of x is nothing else than w times x. And so x is a yeah, x is a column vector, w is a row vector. So I'm taking the inner product between those two guys. And, or more general, if I'm putting in here not just one vector, but several of them, and I put them into a matrix, then of course I have the same relation between the output matrix and the input matrix. So this is now a p times n matrix. This is a 1 times p, and so this here is a 1 times n matrix. Okay, and so yeah, now the question is, given x's and y's, what is the best w to model this? This is linear regression. Yeah, okay, and so of course we also need a model. I mean, so what we want to do is we assume we have a model which gives me y in x, and then this model also has a noise, which means I'm measuring y's depending on x, which are also noisy, and then I want to find the best linear relation between them. So assume, so we have a linear relation between output and input, but if I do measurements, I also have some noise, because otherwise it would be trivial. I have a linear relation, and I want to find the linear relation, and without the noise, I mean, this is not so interesting. So I'm trying to approximate the noisy linear relation by a linear relation. That's what I'm doing here. So I assume we have a linear relation, but noise. So this means that, let me say, the y hat, my measurements, so if I have my data x, then the y hat, which I observe, are of this form. Okay, so without the noise, the relation between y and x is just this w, but now I observe, given x, I observe the y hats, which are perturbed by a noise. Let's say the noise is just a Gaussian noise or so, and then I want to find between this and this a linear relation. I want to recover this w, which I don't know, by just measuring those things. So we want to find the best w, let me call it w hat, such that we have that this y hat is actually w hat times x. I mean, the functions which I consider here are just functions of this form, with a linear guy in between, corresponding to some measurements. I want to find this, and so I'm given the x's, and I'm giving the y's, which are actually related by this, and I want to find this here. And of course, I mean, what I have here is of course a system of linear equations. But maybe we should think, what is the size of them? So x, let's say, is a p times n matrix. So I mean, our data are always p-dimensional, but I have n of them. That's our data matrix. I have n of them. Then the y hat. So this is a 1 times n matrix. So the output for each vector here is just a number. Okay, so I have here n numbers put in a vector, and so this w hat here, this is my column vector, which is also a p-dimensional vector. Okay, so what I have here is this here is 1 times n. So I have n equations, and I have p variables. So I mean, those here are matrices, and I mean the unknowns are those guys here. The w has p components, so I'm looking for p variables, and I have n equations. And now, of course, it is clear that what I get depends somehow whether I have more equations than unknowns or the other way around. Or maybe in the case when they are the same, this is a very special one where maybe the solution is unique. And so we have here somehow also two different regimes, and they will somehow correspond to the regimes which we have there. So we have here, this is a linear system of equations, linear system of equations, and I have n equations for p variables. Okay, and now of course, depending on whether n is less than p, so I have, less data than I have dimension of my space. So then the system is underdetermined. Determined, and if n is bigger than p, so I have more measurements than p, then it is overdetermined. And the solution of this problem for both cases will of course be somehow different. So I mean it's just linear algebra. I mean I have a system of equations, but okay, in one case it's underdetermined, in the other it's overdetermined, and so maybe we consider those two cases separately and try to see what we can get there, and whether we can maybe get something like this. Okay, and so let us start with the overdetermined case, which is more like classical. I have enough data, more than I need. So the overdetermined case, so which means n is bigger than p. Okay, and in this case, I have more equations than I have variables, which means in general I will not have a solution, because I mean I have too many equations which contradict each other. I mean this is just yeah. So this what I want to solve, y hat is w hat times x will typically have no solution, just because x is a mapping from p to n, and so the range of this mapping is just p-dimensional. So if I take on the other side something in the space, this will usually not be in the range. Okay, and I mean this is a classical problem. Instead of saying, okay, I don't have a solution, I mean I want to find a solution which is as good, which realizes this relation as good as possible, and this is the method of least squares. Okay, and so essentially this is saying that okay, I cannot satisfy this equation exactly, so I'm trying to find a solution which satisfies it as good as possible, which means that the mistake I make by comparing y hat with w hat x should be as small as possible. And this means this is the same, that I'm taking somehow, I'm not trying to find here is this image, I'm not trying to find the y hat, but I want to find the projection of y hat onto the range of x. That's classical things. This is the method of least squares, and actually the equation which you solve instead is what is called the normal equation. So I assume that more or less you all have seen this, but maybe just what you are doing is, so I want to look on this. This doesn't have a solution. In general, of course, if the noise would be 0, then there would be 1, but then of course my x data would also not all be independent. Okay, but in general there is no solution. So instead of trying of this, we try to solve a weaker equation, which I get from this by multiplying this with x transpose. So I mean I can multiply this equation with x transpose on both sides, then I have w hat x transpose, and so if I have a solution of this, I also have a solution of this. Okay, but this here I cannot go the other direction. If I have a solution of this, I don't have a solution of this. I only have a solution which approximates the solution here as good as possible. Okay, but so that's what I want to solve, and this is this normal equation in the context of the least square method. So this is what is called normal equation in this context, and it characterizing a w hat for this original problem. I mean there is no exact one, but you can find one, the unique one, such that the difference between y hat and w hat x is as small as possible, is minimal. That's the method of least squares. And here we take the Euclidean norm. Or if I have matrices, it's the Frobenius norm. Okay, so we instead we want to solve this, and this is now okay, because now I have to invert this matrix, and x times x transpose. So what is this? So x transpose. So this is a p times p matrix. So x is p times n, x transpose the other way around. So if I multiply them in this order, it's p times p. And this is typically an invertible matrix. So if the rank of my matrix x, x is a rectangular matrix, so the rank of this can, if p is smaller than n, the rank of this can only be p. Okay, but then that's okay. So p, so this here is typically invertible if my original matrix was had rank p, but which is usually the case. So we assume, we have generic data where the data are not dependent from each other, but they should be independent. So this is if the rank of x, which is p, and this is smaller than n. So if I do it the other way around, then it would not be invertible. But if I multiply it in this way, so that I get a p times p matrix, which is the smaller of the two numbers here, then this is typically invertible. Okay, and this means I can just solve this equation here by multiplying the inverse. So thus my omega hat is nothing else than y hat x transpose, and then I bring this x transpose as the inverse to the other side. X transpose inverse. And so this is my solution. That's the solution which is given by the least square one. Okay, and so now we have a solution, or we have this in a sense is the best we can do to approximate the given data by linear relation, even if there's no linear relation, but the mistake we made is as small as possible. And so we can approximate this relation here by this linear one. Okay, and then of course the question is, what we really want to estimate is this w, the linear one. And we have now said, okay, the real w, we estimate this by this w hat, and we want to know how big is the mistake which we have made. And of course, this should be as small as possible. That's the idea, that we want to approximate our setting by functions from our class, such that the error which we have made is as small as possible, at least in an average sense. Of course, if I have noise here, I should average at some point over the noise. Okay, but so this means we should look what is our mistake. So thus we have made the error. So this is the difference between w and w hat. And those are vectors, so I'm taking here the Euclidean. It's always the L2 norm which I take. That's also what you take in the least squares. The mistake which you make, you count it in the Euclidean norm. It's the sum of the squares of the difference of the components. Yeah, okay. So what is this? Maybe I take here the square. Yeah. Okay, so this is the w, and the w hat we have just chosen in this way. So this is y hat x transpose times x transpose to the -1. Good. Okay, and now of course the y hat, which we get if we put in x, is given by the relation of this. So the y hat, this here, this is w x plus n. The y hat. Okay, now I can plug this in. So what do I get then? So of course I get, okay, this W. Then I get here a sum of two terms. So the first one is minus, so it's W times x transpose times x transpose to the minus 1. Okay, and then I also get minus the term where I plug in the n for the y hat. So I also have minus n times x transpose to the minus 1 squared. Good. Okay, here the first term you see, I have here x transpose. Here I have its inverse, so this is just the identity. This is just 1. So I have just here w. And this w and this w goes away. So this means this part here really gives me the right prediction. It's only that the noise is the problem. If I don't have noise, then of course I just get the correct solution. But if I have noise, I mean the data which should be linear are suddenly not linear, not on a linear line anymore, because there is noise, and I'm trying to approximate them by a linear line as good as possible. Okay, but I mean, this as good as possible might not be the original W, but I have made a mistake which comes from the noise. But the question is, can I see how big this mistake is? Okay, and so this goes away. So it's just that the mistake, the error, comes from the noise. So it's just n. Okay, the minus doesn't play a role for the norm. So I have x transpose to the minus 1. I have the norm. Okay, and this norm, this is the Frobenius norm. Okay, I mean this. Let me see. I mean here. Okay, those are vectors anyhow. And of course, I mean this is also just a vector. Okay, so this just means it's just the sum of the squares of the component. But now if I start maybe to move things around and I multiply in other orders, then I might get bigger matrices in between. But it's always that the norm which I consider is the sum of the squares of all the components, which is the Frobenius norm of a matrix. Where I just consider everything as a vector in a big dimensional space. Okay, but anyhow, so this here, this is the norm of the squares, and I can actually write this as this guy multiplied with its transpose, because the norm, I mean this is a vector, and the norm squared is just the inner product of the vector with itself, but in my vector writing, this is just multiplying the vector with its transpose. And I don't even have to know whether it's a vector or not. I just multiply this with its transpose, and this is the square of this. So what I have here is this guy here. So it's n x transpose to the minus 1. And then I multiply it with its transpose, which means I change the order. This guy here doesn't change under the transpose. So it's x transpose to the minus 1. And then I get here an x. So the x transpose, this is an x, and then I multiply it with the transpose of the noise. Yeah, okay, and now, so you see I have here a product, I have here the noise, and here the transpose, and here in between I have something else. And now we should see, can we calculate this? And maybe you remember that we had, in some calculations, we had these trace formulas, that if I take a Gaussian noise, and I take the vector and I take the transpose, and in between I have something, a matrix, which is maybe deterministic or independent of the noise, then what do I get? I get just the trace of what I have in between. And so now, of course, we have to assume something about the noise. And I assume, of course, it's a Gaussian noise, and it has a given covariance, and then this guy here is the trace of what I have in between. Yeah, so I assume that my noise is distributed as normal, this means 0, and covariance in matrix. So it's a Gaussian vector in R to the, let me see, so where are we? In R to the n. Yeah, so the noise is, so for each component of y, I have a noise, I have n components, so it's in R to the n, and I assume it has a given covariance here, which I call sigma squared. So this is a Gaussian noise. Okay, now I average the mistake which I have made over the noise. Because, I mean, on average, I want to understand what is the mistake which I have made. So I take the average of this W minus W hat squared. So this is the average, and this norm we just have calculated as n xt x xt to the minus 1, and then I have it here twice, minus 1, so it's just x transpose to the minus 2. And then I have x and nt. Okay, and now we have seen in this trace lemma or whatever, that if I take the expectation of here a Gaussian vector with its adjoint, that I just get the trace of what I had in between. So this was actually 4.6. This is yeah, okay, and I get the sigma squared. Yeah, I think there we took standard Gaussians, which have variance 1, but of course the point was that it was the second moment between this and this comes out. So we have here the sigma squared, and then we have the trace of what we have in between. And this is xt, x, xt to the minus 2, x. Good, yeah, okay. And now we have a trace, so we can move this x here to the other side, which changes maybe the size of what we have, but nevertheless, I mean, trace of AB is a trace of BA, independent of the size of the matrices. So even for rectangular matrices. Yeah, so this is the trace of, so I bring this here, so I have x, xt, and I have x, xt to the minus 2. And now, of course, you see this x, xt is the same as I have here with a minus 2. So 1 goes away. So I'm just left with sigma squared, the trace of x, xt to the minus 1. Okay, and maybe in our asymptotic regime, I mean, we want to understand what is this, and we want to understand it, let's say, asymptotically. And there, yeah, if we now assume that x, the data which we have as input, if we also take them randomly, and we take them with a Gaussian distribution, we have here essentially our Wishart matrix. Okay, so I mean, I should put a 1 over n here, and maybe the trace in the limit, it should be the normalized trace. So let me rewrite this in this form. So what I have here is the sigma squared, and then I have here p divided by n, the trace, because those are p times p matrices. So the trace is a trace of p times p matrices, and then the normalized trace is 1 over p times the unnormalized one. So p times the normalized trace is the unnormalized trace. And I also want to put a 1 over n here. So I have here the 1 over n x transpose to the minus 1. Because this 1 over n with this minus 1 comes out as an n, so and it's cancelled by this one. And now you see it's quite good, because p over n in our regime is gamma, so this goes to gamma, and I mean this is just our ordinary Wishart matrix, of which we know what happens in the limit. Yeah, of course, if I now assume that the x have Gaussian distributions, but of course I must make some assumptions on the input which I put in. So maybe assume x is our standard Gaussian random matrix, where all entries are independent and all have variance 1, then this guy here is exactly our Wishart matrix. Then, which we call usually sigma hat. So this is 1 over n x transpose is a Wishart matrix corresponding to the covariance 1, and of which we know that if n goes to infinity, with this going to gamma, has a Marchenko-Pastur distribution. And then, so what this tells us actually is, so if I let now n going to infinity such that p over n is gamma, then this converges to gamma times, yeah, and I mean the trace of this guy here. This is now the resolvent at the point 0. I mean the resolvent was 1 divided by my matrix minus the argument, and if the argument is 0, it's just the inverse of the matrix. So this means we really can relate this in a limit with a quantity which we know, namely the Stieltjes transform of Marchenko-Pastur, because this is the Stieltjes transform of Marchenko-Pastur at the argument 0. So this error, let's say En, and maybe now we average also over X of W minus W hat. This converges for N going to infinity, but P is gamma times N, our usual regime. Yeah, this converges to sigma squared. Then I have gamma, and then this guy here is the Stieltjes transform at the argument 0. S of 0. Where of course the S transform is the S transform of Marchenko-Pastur. So maybe let me write it down again just so that we remember. So S of Z was integral 1 T minus Z Marchenko-Pastur density integration over T. Okay, and of course in the beginning this was only defined in the upper half plane, and now I'm going to the real axis. Okay, but in this case we have a density, which means this Stieltjes transform has a continuous extension to the real axis. So I mean this S of 0 makes sense, and the equation which we had for the Stieltjes transform involving just sets from the upper half plane is also valid for this extension to the real axis. So again we can get this information out of our equation for the Stieltjes transform. So this is the Stieltjes transform of the Marchenko-Pastur, and as we already had at the beginning, yeah, I mean I could calculate the Stieltjes transform by going to the explicit form, but again it's much better to go to the equation, because I can just plug in 0 in the equation and see what I get for S of 0. Instead of trying to write the solution for general argument set and then plug it in, and because we have square roots, one has to be careful what this really means. Okay, so I mean our equation for the Stieltjes transform was 1 plus Z times S of Z. This is S of Z divided by 1 plus gamma S of Z. And now if I plug in Z equal to 0, this term goes away. For Z equal to 0, I get that 1 is equal to S of 0 divided by 1 plus gamma S of 0. Or, of course, I can solve this for S of 0. So this means S of 0 is 1 divided by 1 minus gamma. Okay, and so this means I know this very well, again, from the equation of the Stieltjes transform for Marchenko-Pastur. So I have the expectation of the error which I make in this overdetermined regime is sigma squared gamma divided by 1 minus gamma. Okay, and this somehow is like this. I mean this starts here at 0 and then explodes here at 1, and the point here is 1. And 1 is the point where n is equal to p, which means it's the point where I have as many datas as I have parameters, in a sense. Okay, and there I really have this explosion. So this is the point where my equation is not overdetermined anymore, but where it's exactly solvable. But an exact solution is actually not a good thing, because the noise makes it all over the place. So the prediction power for an exact solution at this point is not, I mean, yeah, I get something which doesn't tell me much about about this one. Okay, so this is somehow okay. In this case, of course, the best would be here very small things. So I mean, this is a very simple example, but still it shows somehow this behavior here. Okay, and then next time, of course, we want to look on the other side, namely if my system is underdetermined, which means it's not a unique solution, but there are many solutions, and then of course I must decide which solution do I want, and then if I do the right thing, I will get something which is on this side, or which corresponds to this side, and also shows a behavior like this. But that's we want then consider next time. Good. Okay, so this hopefully shows you that okay, it's a very simple model, but we can make some kind of calculations which at least give us a feel. Okay, at the moment it just gives us a feeling for this side, which is the classical side. Maybe next time we should see what happens on the other side, that this is really a good thing to look at. Good. Okay, that's it for today.